In this lesson, we'll talk about factors that influence motor failure. Here's a curve that represents the failure probability of any motor. Initially, when a motor is manufactured or repaired and then installed, there is a period in which the probability of failure is high. Some reasons for this is the possibility of any manufacturing defects, shipping damage, or storage degradation, as well as installation problems. After some period, that probability will decrease and remain low throughout the life expectancy of the motor. And at the end of life, the probability of failure again increases. This region is called the end of life region of the motor's insulation system. And we want to be able to identify a motor that has entered this region and replace it prior to failing while in service. A motor that fails in service causes unexpected downtime as well as possible severe damage during the fault, and both correspond to dollars lost. Another way of looking at the life expectancy of the motor is to trend the expected dielectric strength of the winding insulation. Dielectric strength of insulation refers to what voltage will the insulation withstand before failing. When the new insulation system is new, the voltage required to break down the insulation is very high, many thousands of volts. As long as the motor is operating within rating, the breakdown voltage remains very high until, through natural degradation, the breakdown voltage begins to decrease. When the breakdown voltage reaches the voltage level that the motor sees in operation, the insulation will fail and the motor will have to be replaced. And again, we want to find the degradation well ahead of reaching these lower levels. We want to find it up here in the nose of the curve. This is why high voltage testing is necessary rather than only using low voltage. Low voltage testing is considered to be at or below the bus voltage that supplies the motor. Where do motors fail? Well, I've seen many studies that agree very closely with these statistics. IEEE performed this study in 1990s. They said bearings were 44% of the failures, rotor were 8%, stator windings were 26%, and other were 22%. So if we understand this, we can reduce our unexpected motor failures in a mill by almost 30% by simply performing effective motor testing. A factor that influences motor life is thermal aging, and when a motor's temperature exceeds its rated insulation temperature, it can have detrimental effects on the motor's performance and lifespan. The insulation materials used in motors have temperature limits. Exceeding these limits, even for short durations, can accelerate the aging process of the insulation. A rule of thumb is that for every 10 degrees C increase in temperature, the rate of degradation is doubled. Conversely, for every 10 degrees C cooler, the insulation life is doubled. Some people feel this doubling effect has been proven inaccurate. However, we can accurately say an increase in temperature negatively impacts the lifespan of the insulation. Another factor is the effects of contamination buildup on the windings. Chemicals that are deposited onto the insulation attacks the insulation. And this also builds layers that thermally insulate the insulation, causing heating of the windings. Contamination and moisture lead to tracking along the surface of the conductor. Any exposed copper part can track to ground in this fashion, and that bypasses the insulation. This causes problems when attempting to measure the resistance of the insulation when it's being bypassed from surface leakage that's caused by the contamination. Another factor is mechanical. During starting stress, the winding could move. This movement degrades the insulation. Thermal growth is another means for mechanical erosion of the insulation. And over voltage is a major cause for insulation failure. Insulation will be electrically stressed during high voltage events. There are several sources for high voltage stress. Some include lightning, operating on a variable frequency drive with fast switching components such as IGBTs, and what we call switching. Switching is the act of starting and stopping the motor. During these events, voltage spikes as high as 4 times bus voltage can be felt on the windings. Static low voltage and high voltage testing will actually serve to quantify these effects. Anytime current flows through windings in a motor, resistance in the wire as well as other losses cause heat to be generated. One of the key components affected by this heat is the insulation system of the motor windings. How much heating can insulation withstand? Well, NEMA MG1 is the standard for information concerning performance, safety testing, construction, and manufacture of alternating current and direct current motors and generators. NEMA MG1 standard establishes 4 classes of motor insulation. Each class defines the insulation system's ability to endure a specified temperature while providing a specific operating life or temperature rating. Major and most commonly used motor insulation classes include A, B, F, and H. Understanding the differing insulation classes and limitations for each is an essential part of an effective reliability program. Operating motors within the design parameters of their insulation class can yield significant increase in reliability and motor life. The maximum permissible winding temperature rating includes 3 elements: the ambient temperature, the allowable temperature rise when operating, and a hotspot element that must be included for areas that may be heating more. With Class B motor insulation, the maximum permissible winding temperature is 130 degrees C. Now that is made up of ambient temperature of 40 degrees C, allowable temperature rise of 80 degrees C, and an allowed hotspot over temperature of 10 degrees C. With Class F motor insulation, the maximum permissible winding temperature is 155 degrees C. Again, an ambient temperature of 40 degrees C. This time the allowable temperature rise is 105 degrees C. And again, the allowed hotspot over temperature is 10 degrees C. And this class consists of dielectric materials like mica, asbestos, and glass fiber. Class H motor insulation, the maximum permissible winding temperature is 180 degrees C. Ambient of 40, allowed temperature rise is 125 degrees C, and the allowed hotspot over temperature has increased from 10 to 15 degrees C. The majority of all motors are designed for a 40-degree ambient and an 80 degrees C rise when operating at 1.0 service factor or full load. Motors rated with a 1.15 service factor can be overloaded by 15%. With the typical motor design and operating at full service factor, the temperature rise is approximately 105 degrees C. Therefore, when operating the motor at 1.0 service factor, the winding temperature is 130, and operating at 115 service factor, the winding temperature is 155, which means when operating at 1.15 service factor, you're at the Class F insulation maximum permissible temperature rating. And this can result in a 3-year life expectancy of the winding. A motor's insulation system should have a relatively high temperature capability, and the motor should operate at a relatively low operating temperature. And this provides a thermal margin in the event of motor's overload or severe starting duty or some safety margin. So a motor design at Class B insulation limit can have a Class F insulation system installed, and this gives a margin from a motor operating at full load temperature and the insulation temperature rating. There are exceptions, like when trying to match an old design. A manufacturer may not be able to meet the frame requirements without an F rise, In that case, they would use a full H-system insulation inside the motor. So is it okay to continuously operate in the service factor? This is what MG1 says. All motors shall be rated for continuous duty and shall be designed with a 1.15 service factor, but shall operate normally at 1.0 service factor or less. Operating above the 1.0 service factor should be limited to intermittent periods of time without damage during unforeseen circumstances. If base loads above this 1.0 service factor are expected as a frequent condition, the next horsepower rating should be used. Service factor is included in the motor rating for power quality issues and not for continuously operating above the motor horsepower rating. This graph indicates the relationship of insulation life expectancy and temperature. Each curve is a different insulation class. Here's a Class A, Class B, Class F, and Class H. This graph is based on the idea that for every 10 degrees increase in temperature, the rate of degradation is doubled. The 10 degrees C increase equal half-life rule is based on applying the equation which relates the rate of chemical reactions to temperature to failure mechanisms that will occur. Whether the half-life rule is entirely accurate or not, maintenance experts do agree that excessive heat will cause rapid deterioration of the winding insulation within motors. Let's first examine the curve for the Class F insulation. We see that the majority of all motors are designed for 40-degree ambient at 80-degree rise at 1.0 service factor. So operating the motor at that rating, 120 degrees, correlates with a life expectancy of 250,000 hours or 28 years of life, which would be 250,000 hours. If the temperature is increased by 10 degrees to 130 degrees, this curve indicates a 50% decrease in motor life or 125,000 hours. When operating at maximum Class F temperature rating of 155 degrees C, the motor life drops to 20,000 or 25,000 hours, which is only 3 years. We've gone from 28 years to 3 years by operating the motor continuously in the service factor or at full Class F temperature rating. Another cause for thermal failure is current imbalance. A 3% voltage imbalance will cause a 18 to 20% current imbalance and a 25% increase in motor heating. And this condition is not sustainable and will eventually lead to iron overheating and significant rise in motor temperature. That, as mentioned above, may not be detected by the thermal protection. Motors operating with current imbalance must be derated. Derating is the operation of a motor at less than its rated maximum capability to prolong its life. To understand insulation construction in the motor, let's look at how a stator core is constructed with slot liners installed. Here is a stator core made up of laminations. The laminations are stacked on top of one another to form this core. In the slots of the core is liner paper or slot liner paper installed. This is Nomex insulation that's installed in these slots. On random wound stators, after the slot liner is installed into the slots, the windings are then installed into the slot liners. And then top sticks are installed over the slots and over the coils. The ground wall insulation consists of the slot liner paper and this enamel varnish that you can see, this orange color varnish on each conductor. Both added together make up your ground wall insulation. Another type of stator winding would be Formed wound. Here are medium voltage form wound coils that are installed in the stator core slots. Here we can see different failure modes of windings. First, turn to ground is when the turn and ground wall insulation has failed. A turn to turn is where adjacent turn insulation has failed but not yet transferred to ground. A coil to coil is when a larger group of turn insulations has failed. And then a phase to phase is when the turn insulation and phase insulation have both failed. No matter what type testing program we have implemented in our facility, it must be capable of interrogating each type, as well as identifying degradation of each type failure. Simply testing the ground wall integrity is just not good enough. This picture indicates where a turn to ground fault has occurred. It is at a common location called the slot exit. Coils that may have movement can easily cause failures here where the coil is exiting the slot. Here's a similar fault of a ground wall insulation at slot exit. Do you notice anything wrong with this picture? Absolutely. The windings are plugged with pulp fiber. All cooling air is blocked, which contributed to overheating and insulation failure. Earlier, we mentioned surface leakage, and we're going to talk more about it throughout this course. Any exposed copper part, such as a connector, can track to ground along a path on the outside surface of the insulation. Surface leakage bypasses the insulation, and this causes a problem when attempting to measure the resistance of the insulation if it's being bypassed from surface leakage caused by contamination. 80% of stator winding failures start out as a turn-to-turn fault. That's not just me talking. This is General Electric's paper documenting and saying the same thing. Most will fail to ground in the slot and some phase to phase, but the root cause will be turn to turn. They may fail somewhere else, such as a phase to ground, but most start out as turn to turn, and that's because the turn insulation is the weakest insulation in the motor. And how long would you expect a turn to turn fault last before turning into something large enough to trip the motor? Well, the answer is, according to IEEE, a welded turn-to-turn fault on an AC induction motor will escalate and burn through the slot cell liner to ground within 15 minutes. So an AC winding cannot survive when turns begin to burn together and weld together. With an induction motor and an alternating current is flowing, a turn-to-turn fault creates a shorted coil with no impedance, and the adjacent turns with AC current flowing will induce current into that shorted coil. With nothing to limit current, the heat will build into a shorted coil, and the heat will burn its way through the adjacent turns, all the way through the adjacent turns and until it contacts another phase or ground. Turn insulation is the weakest insulation in the motor. Turn insulation failures modes include chemical deposits will form on insulation breaking down its insulation properties. Movement of coils during starting or startup rubs turns together, and possible damage when being wound. Also, variable frequency drive voltage spikes. All these things contribute to turn-to-turn failures. And here's a cross section of a form coil with many turns. Each of these little copper sections are turns. And the insulation that surround these individual turns is very small in respect to the ground wall insulation out here. Not all coils are the same. Precision coil manufacture and insertion is critical to prevent damaging the turn insulation. In the previous slide, we saw what the alignment of turns inside a coil should look like, very uniform and aligned. Here we see two different type coils. One on the left is a VPI coil that is very rigid, and the one on the right is a B-stage coil. The B-stage coil appears to not be cured properly or not at all, and both have issues with turn alignment. The turn seems twisted, which has narrowed the spacing between the turns, and this lowers the dielectric strength between the turns. Many times it's what we cannot see that can reduce the life of a motor. Not all are the same when it comes to reliability. Voltage spikes damage turn insulation. A source of voltage spikes is called reactance voltage. Well, what is reactance voltage? If a rapidly increasing current is applied to a coil, in other words, a current is increasing or decreasing, a voltage will be generated across the coil by the principle of self-inductance. Self-inductance is the property of a current-carrying coil to resist or oppose the change of current flowing through it. And self-induced voltage present in the coil will resist the rise of current when the current increases. It also resists the fall of current. And this voltage can be very large. The voltage level is determined by the rate change of current pulse, di divided by dt, and change in current over change in time. We call this rise time of the current pulse. This occurs at startup when a cross-line starters operate to close or even open. Soft starters reduce the startup transient, but not the shutdown transient. This transient voltage also occurs with variable frequency drives, which switch the current rapidly and repeatedly. Voltage transients of 2 to 5 times line voltage are very common. This is a primary reason for failure of weakened motor insulations. One of the major sources for the high energy transient is the motor contactor, which is a device that is supposed to protect the motor. When the starter contacts close in the motor control center during startup, they often bounce or chatter, and this means the high inrush current is being made and breaking several times. As a result of interrupting the current, an inductive kickback voltage or voltage spike develops, and large inrush currents along with the high inductance of electric motors are what give these kickback voltage spikes their energy. Now here's a real world scope capture of a medium voltage bus while starting a motor. Not only does this motor see a voltage transient of over 2.2 per unit, so does all the other motors that are connected to this same bus. So this is real world. Don't just take my word for it. This is exactly what happens when motors are starting and stopping. When a voltage spike occurs, the voltage between turns is greatest at the first few turns and decreases the deeper into the coils. Here is what a voltage distribution looks like across a group of coils in a phase winding. It's higher at the lead end out here and lower towards the Y connection down here. Also, the faster the rise time, the more voltage will occur. So if its rise time is 0.2 microseconds, there's a much higher voltage transit that's experienced on the winding turns. Out here, mainly on the early turns, or the lead end of the winding. The majority of turn-to-turn faults start at the first turns in the winding, or what we call early turns. Early turn faults are most likely due to high voltage spikes. Sometimes voltages are described in per unit. This is just a way of quantifying the effects across different voltage class motors. And here's a calculation for an electrical per unit. It is simply the DC equivalent voltage of a single phase voltage to ground. So in a 480 volt motor, 480 volts divided by 1.732 times 1.414 is equal to approximately 392 volts. That would be the DC equivalent of the single phase voltage to ground for that low voltage motor. And for a medium voltage 2300 volt motor, it would be 1877. As stated earlier, motor windings see high voltage spikes on startup, shutdown, and even during normal operation. And worst case spike is 5 per unit, which on a low voltage motor, 1 per unit is 392 volts. So a low voltage motor may experience a voltage spike during startup of up to 1960 volts. Now here's a table of different per unit values based on motor class. A 480 volt motor could have up to 5 per unit, we said, which would be 1960 volts applied on the terminals during starting and stopping. A 2400 volt motor may have as much as 9800 volts, 4160, 16,000 volts. So there's a high voltage potential that's possibly going to occur at the motor terminals on just simply starting the motor and normal operation of the motor. According to Paschen's law, it requires 325 volts to arc across the thickness of the typical turn insulation. Therefore, we must interrogate our turn insulation to a minimum of 325 volts. So now that we understand more about what a motor sees during normal operation, let's revisit the life curve and this time insert the voltage spikes that are seen during starting the motor. We can see that if insulation dielectric drops below not only the bus voltage, but these voltage levels that it sees during starting and stopping, it could fail. It has a potential of risk of failure, not only here, but as well up here. Megger performed some dielectric testing of very fun materials to examine, such as toilet paper, electrical tape, Nomex paper, which is our ground wall slot liner, and other materials that would be fun to examine. And here are the results of those tests. Toilet paper withstood up to 1980 volts before breaking down. Nomex was over 20,000 volts and it broke down. The magnet wire, which is our enamel wire used in random windings, was around 5,000 volts right here. Also notice this column that says linear or nonlinear. Linear means the leakage current followed the steps in voltage in a linear manner before the failure. Nonlinear means it did not. Instead, the leakage current was increasing at a faster rate than the previous steps, while steps in voltage occurred. So nonlinear result was trying to show us that it was about to fail prior to failing. When a low voltage motor is manufactured, NEMA says the wire must have 6,000 volt AC RMS insulating capability. Well, 6,000 volts AC RMS is equivalent to 8,400 volts DC. So this means our turn insulation should have at least 8,400 volts DC dielectric just for that turn insulation on a low voltage 460 volt motor. If you take the 8,400 volts of the turn insulation, or this magnet wire in this case, with a random winding, and add the 20,000 slot liner dielectric strength, the total combined ground wall insulation for a low voltage 460 volt motor is 28,400 volts.